So I know that you had your quizzes due yesterday. I have not had a chance to actually physically grade them, but I did look at them. And there's one problem that I want to touch on today. And then tomorrow I will grade your quizzes and give you feedback individually. And so there was one problem that was universally kind of like struggled on, and then the rest of them was a blend. And so I felt like it was better if I just gave individual feedback, but then covered this one problem with the group. So I'm going to do that. Also, I know, and I'm so sorry that you had your linear activity was due last week, right? And I still haven't had a chance to get to it. That is on my to-do list for tomorrow. So please have keep your eye out for feedback tomorrow from that, because I want you to have that in time for when you're working on your exam next week. Let me keep, sorry, I'm taking attendance as people are coming in. So speaking of the exam, it will release, so the exam is next week, right? I have posted a review assignment. It is optional. That is in Eagle Online, which so much easier if I just show you my screen instead of trying to explain. Hold on one second. Okay, so where can you find the review? So we go to content and scroll down. You're going to see exam 1 here. That's listed. Okay. I have a review posted and I have a set of solutions posted. By no means is the review like the end all be all. This is exactly what's on the exam. Okay, like it's a set of practice problems that is a good coverage of things that could be on the exam if you're looking. And so the solutions also are just going to give you, well, here I'll show you what I'm talking about. They'll just give you like a specific number. It's not going to walk you through how to do it, because again, the exam is open notes, and so you shouldn't be like having this up to look at the steps to how to solve it, right? If you are looking for additional problems even after you complete this, like I said last week, in the table of contents, in our content, we've got these additional practice and videos. You can go to those and find the blank lecture slides that I did from when I taught it in person last, which was I think 2019. And you can practice those problems. That's definitely something that I suggest as you're preparing for the exam in 1B. Homework 6 I'm going over today, which is the applications of exponential and logarithmic functions. I really suggest that you go into this applications of exponential and growth, this extra file, and work on these extra practice documents that I have in here, because again, having more practice is always going to be helpful beyond what we just have in our homework assignment. Okay, so I think that you will find that stuff helpful as you are working on homework 6 and working on preparing for the exam. So again, I'm saying that when you're working on homework 6, obviously watch the main set of videos that we have there. But I have found that students really benefit from going in and looking at this additional section here that I have laid out. So, questions for me before I jump into what we're going to do today? Luke, I'm happy to see your thumbs work. I appreciate it. Mobility is very important.
Work well.
Ambidextrous mobility.
Yes,
Great. All right, let's change screens. Okay, so the first one we have is 2 to the x equals 5 to the x. And this is kind of a weird problem because what we're saying here in number 1, this is more just like kind of a discussion of how we would think about this. We're saying that 2 to some power has to also equal 5 to some power, right? It's kind of a weird idea. So is there any number that we know of that I could plug in for x there that would make that true?
no.
Okay, so what like what number could we pick?
Oh, we could
I'm
do
not saying you're wrong. I'm just saying
could-
like how could we think about this from a exploratory standpoint?
we
Okay, so I've got some suggestions in the chat. So I'm seeing, what if we let x equal 5 or x equals 0? What else could we try? Anything's gonna, we're just, one of the things I like to tell students is if you're faced with a problem that you don't know what to do, like you're looking at it and you're like, I have no idea. Try some guess and check, right? Like try to just put some numbers in to see how things are working. So if I put x equals 5 in, see, these are the things we're going to try, right? Well, we've got 2 to the 5th, and our question is, does that equal 5 to the 5th, right? Well, 2 to the 5th, 32, yes? Is my mental math correct? Yes, it is. So 32 and 5 to the 5th, that's significant, isn't it? That is 3,125. So that's not going to work, right? But it's a good guess, right? Like we have to start somewhere. If we put 0 in, 2 to the 0, and the question is, does that equal 5 to the 0, right? Okay, well, 2 to the 0 is 1 because anything to the 0 power is 1, right? Here's our little reminder. Anything to the 0 power equals 1. Okay, so 2 to the 0 is 1. 5 to the 0 is also 1. So that is where it's a true statement, right? So one of the things that it's easy to forget that we have been talking about here is that these are, I know that it's just an equation with a single variable, right? But if we're talking about equality, we have experienced so far taking one equation and setting it equal to another equation, right? Through substitution. So if we think about these as f of x equals 2 to the x and f of x equals 5 to the x, then we can graph them, right? And so again, when you're looking at solving these problems, sometimes the algebraic steps don't come to us initially, right? But if we think about it from a standpoint of, oh, I've graphed functions, we're looking for where these two things are equal, which means we're looking for where do they intersect, okay? So if we adjust our screen so we can see everything, hold on one second, let me bring over my Desmos screen. Okay, so now I go here and I go, okay, well, we're going to do f of x equals 2 to the x, okay? I don't know why I decided to do capitalization. Let's fix It's because I have the thing on. Hold up. There we go. And then we're gonna do f of x equals 5 to the x, okay? And like I said, when we're looking at solving this, we're looking for where do those functions overlap? And they're gonna overlap right here, right? At this point right here, okay? And if we hover, we can see that we get this ordered pair of 0, 1. Well, what that tells us is that for the value of x, that makes them both, value of x equals 0, excuse me, that makes them both true, which we saw when we did the calculation right here, right? When we let x equal 0, f of x is equal to 1. That's what that ordered pair of 0, 1 is indicating. Now I know that the original was that I just wanted 2 to the x equals 5 to the x, and what value of that is true. So really, what value of that is true? X equals 0. That's what makes that statement true. And when I say statement, I'm talking about this original equation. So going back to this idea of graphing can be really helpful when you are trying to either get a picture of what's happening here to begin with, or you're trying to check your answer. Did I actually do this right? Okay, so like when you're solving these on your exam, I'm going to want to see the algebra. I'm just going to warn you, I want to see the algebra. But if you also show me, hey, I graphed it to figure out if my solution was accurate or not, that's really helpful information, because again, that lets me know that you're seeing the connection between graphing something and what the intersection means in terms of the solution of the equation, okay? So if we look at number two, we want to solve for x, right? So in order to get to x is in the exponent, right? So what are steps that we could take to get to that? What do we need to do here? What are we thinking?
you say that again?
So I'm looking at number 2, right?
Oh, okay.
I'm trying to solve for x, right? So I need to get to that variable eventually. There's a fair amount of steps that I can take to isolate the term that x is in. So
Yeah.
what would be some of those steps I can take to get to where my variable is?
You could subtract 4 from both sides and then divide by 3 on both sides.
Okay, so we're thinking about trying to isolate it, right? And so when we're isolating, we're going to undo that addition and subtraction first, and then we'll undo the multiplication and division. So we're going to subtract 4 from both sides, bring down this term, and I'm going to get 3 times 1.4 to the x equals 60, and then we want to divide by 3. And that gives me 1.4 to the x equals 20. Now, from an algebra standpoint, we have an exponential function that we need to undo, right? And in order to undo exponential functions, we use the inverse, which is the logarithm, okay? So what I want to do here is I want to take the log of both sides. So what that's going to look like is I'm going to write log of 1.4 to the x equals log of 20. Now, last week we talked about the power rule, and when you've got that exponent up here, you're taking the log of a value being raised to the exponent. We can bring that exponent down in front of the log. And this is the key piece, because bringing that down in front is what allows us to get the x out of the exponent position. Because now what I can do is I can divide both sides by the log of 1.4. and I get x is equal to the log of 20 divided by the log of 1.4. So if I go to Desmos, always wait till the very end to convert those logs into numbers, because remember the log of 20 is saying 10 to what power equals 20, right? That is a actual number. And so you want to wait till the very end when we're at the division step to simplify this. So I get x is equal to 8.90. I'm just going to round to 3 decimal places. So how can I use that graphing step that I used in number 2 to help me check my work? Or excuse me, not number 2, number 1. How could I use that graphing technique to check my work for number 2? Here, I'll zoom out so you can kind of see what we wrote up above.
You could use would you put it the f of x is 1.4 to the 8.903, or is that not right?
That would help us to check if it equals to 20, so we could try that.
Okay.
So 1.4 to the 8.903, and we get really, really close. So that is a good way to check you know, that you've got approximately the right value, right? But when you're checking with graphing the two functions, we want to think about one side is one function and the other side is another function, okay? And so we could check this as f of x equals 3 times 1.4 to the x plus 4, and also f of x is equal to 64, right? Because f of x equals 64 is the horizontal line. We're looking at where is that value, where does that function equal that specific value, and that's going to help us to check our work. So if I clear these out, we can come in and do new functions. So you'll notice that this is what our first function looks like, okay? So it's a real steep exponential growth function. When we're looking at for where it's going to equal 64, we can tell along this axis here. This is 60, that's 65, and that's 70. So 64 is going to be right around here. And so we can see that that value, if we go down below, is close to 10, right? It's on its way to it, but it's not quite there. So if we graph our second function of f of x equals 64, oops. It's going to give us our exact intersection right there, right? It's giving us that 8.903 is the x value approximately, because again, it's rounding it off, but that's that x value that's going to give us a function equal to 64. And again, we can see that x value matches the value we found using algebra. So I'm just trying to give you some tools on how you can help monitor, am I doing these steps right? Because as we're solving these, they are uncomfortable because it can involve things that we're not very accustomed to, right? Logs are, it's an area of math that if you're dealing with exponentials, you have to deal with logs. But once you stop dealing with exponential functions, we're not really talking about them a whole lot, right? And so again, this is a way that you need to learn the algebra of how to solve these by hand. And big old like that I need to see that you can do it by hand, but how can you help yourself as you're doing it? Think about them as two functions, graph them, look at where your intersection should be, okay? So that can help you to kind of guess and check, or not guess and check, I shouldn't say, but at least to determine the reasonableness of your answer. So questions about that process. How does that feel as we're thinking about doing these problems?
Not bad. This is definitely helpful though.
I find the reason I really like it is that I'm a very visual person and I want to, what is even happening? Like, what does this look like? Why are these intersecting? Why is that answer? And it's because, again, you've got one function and another function, and where are they coming together? And we can tell, oh, that's why it's the solution, right? Why X is that solution. It's because that's the X value. This is associated with that Y value. All right. So another exponential function that we deal with is base E, right? We've got these base E functions. And so in the previous example, I used log because we didn't have base E involved. We didn't have the number E. Anytime you see E, you have to use the natural log. Now, what we have here is just standard e to the x equals this value. So we're automatically going to start by taking the natural log of both sides. Now, again, using that power rule, the exponent comes down in front once we take the log. And I have x times the natural log of e equals the natural log of 52.0699. The reason why dealing with e is so nice is this piece right here. Remember the identity that says the natural log of e is equal to 1 because, oh, whoops, let my board catch up. Because e to the first power equals itself. So remember, when we're taking the natural log of e, the question that statement is saying is e to what power equals 1, right? And or e to what power equals itself, because there's this little assumed base right there, right? So e to what power equals itself? E to the first. And so we can replace that natural log of e with 1. And when we do that, we don't really need to have the 1 anymore, right? 1 times x is still x. So we get x is equal to the natural log of 52.0699, which, when we come over to decimals, we get, that is our answer. And you can round these to 3 decimal places, whatever you want. Just go more than 1 is all I ask. On the exam, I'll specify how many decimal places I want you to take it to. Okay, so we're not going to just leave it there in terms of steps. We're going to make it more complicated, of course, because we're getting ready to solve word problems, and the word problems create complex equations, and so we have to be able to solve them, right? So I have 9 times e to the 2x plus 5 equals 25. So again, when you're solving these exponentials, you want to try to isolate everything on one side that the variable is in the exponent. Meaning I've got 9 times this stuff. So we're going to get rid of that 9 first. by dividing both sides by 9. Now, you'll notice I'm going to leave this as 25/9. And the reason I'm doing that is because of the fact that 25 divided by 9 is not a nice decimal. It's a repeating decimal. And so rounding it off will make our answer inaccurate. And so I'm just going to leave it as it is for now. And then we'll deal with it later. Okay. So now that I have e to the 2x plus 5 power, e equals 25/9, our step at this point isn't actually any different than what I did in number 3. We're just taking the natural log of both sides because we're trying to get to that exponent stuff. Okay. Okay, so just like in the previous example, when I take the natural log of e being raised to that exponent, it allows for everything in that exponent to come down in front. Okay, so once we do that, we can drop the ln of e part. And from here, if you want, there's 2 ways we can go. We can now convert the natural log of 25/9 into a decimal. Okay. Or we can leave it as it is and wait till the very end to do it. So, if we were to convert it, we would have 2x plus 5 equals 1. And you want to take it out of fair. If you're going to convert this at this point, you want to make sure you're including, you can see I included 5 decimal places. You want to include a fair amount of decimal places. Don't just round it off at like 1.02. That's going to lead you to the least accurate answer, right? The more decimal places you include, the more accurate your final answer will be, okay? And so from here, we're going to subtract 5. And then our last step will be to divide by 2. One of the reasons why using Desmos is really nice is that you can, I don't know if you've figured this out yet, but you can copy the output to use in your next line. And so instead of rounding off, if you had wanted to, you could have clicked on this. Oops. Come on. We're going to do Control C, and then you could have come down here and pasted it. Okay. And then if we and that, again, it just takes your decimal places out farther. If we had not rounded the natural log of 25/9 from the very beginning, what that would have looked like if we'd done the whole calculation as 1, that means we would have had x equals the natural log of 25/9 minus 5 all divided by 2. That's the steps we took, right? We subtracted 5 from that value, divided the whole thing by 2. And again, the beauty of Desmos is it will do all of that as 1, right? I just know that many people are uncomfortable with leaving it in that form, and they're like, I need it to just be a number. But again, if you do it all as one, you'll see you still come up with your same value. Here we go. Negative. And here's where you can see, again, it's so infinitesimal, that rounding aspect. But this is at the very end, you can start to see how intermittent rounding, depending on how many decimal places you round it to, how accurate your final answer can be. Again, Desmos is holding like so many more digits that we can't see within that calculation. And then you're gonna obviously get the difference shows up way down at the end. But that's how you can wait to the very end to have your answer come out. Questions about that?
Nope. Just getting to that point sometimes is the confusing part.
Mm-hmm. And I know you're gonna hate this answer, the only way to get to that point and to be comfortable with that is practice.
Yeah.
And so that's why I'm always like, go seek out those extra problems, go look at those extra sets that I have in there, because doing more practice is the only way to feel more comfortable with it. Obviously, I want you to be practicing in a productive way, right? Like if you're spinning your wheels and looking at it and going, I have no idea where to start, we need to have a few, like we need to talk. But again, once you're like, okay, well, I think I know that I need to do this, and now where do I go from here? And you're feeling more comfortable as you're like walking through the examples, and then you're just forgetting those key pieces. Again, continuing to practice the problems is what's going to help. Okay. We're going to do one more just algebra solving, and then we're going to get into some word problems. So this one is a logarithmic equation. And so looking at this, it can feel uncomfortable as to where to start. And this is an example of our product rule. So if you remember from last week, we talked about the product rule as it applies to logarithms, where it's log of a b is equal to log of a plus log of b, right? And so we can go the opposite direction. The thing you have to make sure is that in order to bring these back together, your bases have to match. If they don't match, if this was say log base 2 of x plus 4 plus log base 3 of 6, there's nothing you can do here to bring them together because the bases don't match. But because these bases are the same, we can apply the product rule to this situation. So we're going to bring these back together. And what that's going to look like is log base 2 of 6 times x plus 4. Right? We had the pieces that were broken apart, and then we brought them back together. And that's going to equal 4. So right now, we're in a logarithmic equation. In order to solve for the variable, we need to rewrite this equation in exponential form. And so if you remember from last week, we're talking about when we're switching from logarithmic to exponential, we're taking the base, we're going to raise it to that power. So we're going to get 2 to the 4th, and we're going to set that equal to what's inside your log, which is this. And then once you get to this step, then it's a little more like, oh, okay. The word log is gone. I can go from here, right? I don't know what it is. Some reason, and I think it's like we've introduced words as part of functions, and like I feel like people I don't know, for years it's always been like I don't know, you know, I have a word as part of what I'm supposed to be doing. But again, it's the idea that this is a function that's happening. So switching it from logarithmic to exponential, we now have this nice exponential equation. And so what I'm going to do is I'm going to stop, and I want you to solve for x and send me your answer as a direct message.
Is a fraction okay?
Mhm.
Okay.
I prefer it because it's a non-terminating decimal.
Okay, sweet. Are we gonna go over that quiz problem as well?
Yeah, I'm getting ready to do it
Okay.
after this because
Okay.
it's a good segue into what we're gonna do next. So yes, it's
Sweet.
still on my mind. Don't you worry.
Just making sure you didn't forget.
I didn't. But I appreciate you looking out for me, Luke. We know that I get distracted.
That's what I'm here for.
All right, so we need to solve this, which means we need to simplify before we can get to our solving stage. When I say simplify, that means we need to simplify our exponent, right? 2 to the 4th, we need to actually calculate that. And so 2 to the 4th is going to be 16. Meaning that 16 equals 6 times x plus 4. And sure, you could divide both sides by 6. That's not going to be real helpful because of the fact that it's automatically going to get you in a situation where your fraction's not going to reduce, right? And so I say, let's leave the fraction to the end. So let's look at distributing first. And so by distributing, we've cleared the parentheses. We can now subtract from both sides. We get what, -8 equals 6x. Divide both sides by 6. And you get x equals -8/6 or -4/3 or -1.3 repeating, right? So the big piece here, the things I want to drive home is we need to recognize when we are using the product rule, right? You need to be able to bring those together. Again, the only reason I was able to do that is because of the fact that our bases were the same, right? So building on that, there was a question on the quiz, and this is not the one I was originally talking about, but it did trigger my brain and went, nah, I should talk about that. So there was, actually, I'm not gonna, let's just do a new page. one of the problems said we have log of x to the 20th y to the 2nd over z to the 11th. And they said, I want you to write it in a log x plus b log of y plus c log of z, right? They wanted you to write it in that format. And so what that's asking us to do is use all of our, what am I trying to say? All of our identities together, okay? And so what we need to do first is we need to recognize that z to the 11th can be rewritten as z to the negative 11th. Okay. And so once I rewrite that, now I can see that I have the product rule happening because it's the product of three values. Okay. So I can break this up into log of x to the 20th plus log of y squared plus log of z to the negative 11th. And so from here, there's the question of, well, what are they meaning by A, B, and C? Okay, and that's where that power rule comes into play, where we're taking the log of a value that's being raised to the exponent, we can then pull that exponent down in front. And so this is going to give us 20 times log of x plus 2 times log of y plus negative 11 times log of z. Because again, we're bringing that exponent down in front, right? That's the power rule. Okay, so they had wanted you to write it in this way, and then they said, okay, identify what A, B, and C are. A is 20, B is 2, and C is negative 11, right? Because those are the values that are in front of the logs, because they were the exponents that we brought down when we broke it apart. So again, those I know that those identities were covered in the lectures, but if you look at last week's notes, I've got them written out right there. They're in a box in last week's notes as well. So that was one of the questions from the quiz. And the one I had originally wanted to talk about, which leads us into, again, taking these situations and writing exponential equations to represent them, was this one. So it said, we've got a function that says y equals f of x, and it's an exponential curve. Please bear with me as I draw this. Looks like that. And they gave you 2 points, A and B. And they told us that A is the 0.03 and B is the 0.212, right? And it says, give a possible formula of the form C times A to the X for the function. Okay. So what do we know, right? So we're writing y equals C times A to the X, right? So first of all, this is an X, that's a Y, right? So let's plug those in. got 3 equals c times a to the 0 power. Again, what do we know about a to the 0 power? A to the 0 power equals 1. So that tells us 3 equals c times 1. If I replace that a to the 0 with 1, right? Which tells us that 3 equals c. Because we have to continue to whittle this down. So we have our final equation that we're writing is y equals some number times a number to the power of x, right? We want to only have our variables be x and y. So knowing that we have that first order pair, we can solve so far by saying, okay, well, y equals 3 times a to the x. Because we've solved for c because of the fact that it goes to that 0.03, right? So once we solve for that, now we can work on using the other ordered pair, right? This is another x and another y value. So if we plug those in, we're going to have 12 equals 3 times a squared. So just as we were doing before, we're going to divide both sides by 3. 12 divided by 3 is 4. And from here, we can take the square root. The square root of 4 is 2. So we are going to use the positive root here, okay? I know that there's both a positive and a negative root. We will limit our answers to the positive root, okay? So why would I want to do that? Let's write our equation and then we'll look at both of them in Desmos. So what I'm coming up with is y equals 3 times 2 to the x, right? So there is my equation. Remember I told you it was supposed to go through the 0.03, and then it's also supposed to go through, let's do y equals 12. And we can see here that it goes through the 0.212 as well, right? Well, what if I had said, well, the square root of 4 could also be -2? What would that look like? Oh, geez. Where is the function? Hold on. Long story short, is it there? Is it matching what we want it to be? Because what happens when we raise a negative number to a positive exponent, or to an even exponent? What do we get?
Positive number.
And if we raise a negative number to a odd exponent?
It's negative.
Right. So the reason we can't use that base of -2 is because ultimately it's not going to give us those same values if we plug them in, because of that positive negative thing. So that's why we want to limit it to a base being a positive. So when we're taking the square root of 4, we're going to limit it to just the positive root. So again, that was one of the quiz questions. And so that's like, it's how we would solve that. That is a way to solve it. Okay. So from here, we're going to move into, again, writing exponential growth and decay models. So this stuff I just copied from our notes yesterday, or not yesterday, last week. But I want to point out another term that gets used for exponential growth and decay models that are not continuous. And that term is periodic. These formulas are referred to as periodic models. And so you may see in your homework and in the practice problems and in the exam, the term periodic, and it tells you to write a periodic model. Okay, so when they're referring to periodic models, these are the models that we're referring to. There are more options. Okay, so if you get into the notes that I have down in the additional stuff, there's a couple of different forms. We're going to limit our periodic models to these two forms, but there are other ones. If you took Math 94 before this class, if you remember when we were looking at exponential growth with money, you might remember we used this one. This might remember that model where we were looking at compounding money, and n is the number of compounding periods in a year. So like when we had if our account balances were compounding monthly, then n was equal to 12. But again, we are going to just limit it to these two periodic models. Okay. Also, sorry about the typo here. We're gonna make that X. So how do we use these? What does that look like? So we're gonna go to the next page. What are we at time? We're like 7 minutes. Shoot. Okay. I always want to tell you too much when we're together. I'm sorry. I'm not good at limiting myself. So number one says a single cell of E. coli divides into two cells approximately every 20 minutes in the right conditions. If a petri dish contains 100 cells of E. coli, how long will it take for the petri dish to contain 400 cells? Again, my encouragement to you is always write out some data to help give yourself an idea of what's happening. So what I'm saying is that at time equals 0, we have 100 cells, right? So if every cell divides into two cells, what does that mean is happening every 20 minutes?
It's doubling.
It's doubling, right? If I go from one cell and each one divides, it's giving me 2 to replace it, right? So then at t equals 20, how many cells am I going to have?
200.
200, right? Because we're doing 2 times 100, which gives us 200 cells. Okay, 20 minutes later, 40 minutes. Now what do I have?
400.
Because we did 2 times the previous, which gave us 400 cells, right? So how can we relate this concept to writing? I mean, we have our answer, right? We know it's going to take 40 minutes for those 400 cells to show up, right? How can we relate this to writing a equation to represent this, right? Well, we know that the original amount is going to be 100, right? That's our starting amount. So that means our P sub 0 has to equal 100, right? And every single time I am multiplying that value by 2, right? So that's going to tell us that our base, so what I'm talking about is if I'm using the formula P sub 0 equals, or excuse me, f of x. Sorry, I'm trying to make sure that I match the formulas we have on our page. P sub 0 e times a to the x, right? So I know that I can say, okay, well, that's equaling 100 times. Now, if I'm multiplying every time by 2, okay, then I can say that a is 2. That's not going to help us in turn. I mean, that is the true statement, but there is an additional piece that we have to take into account here, because let's say I wanted to write this model in terms of X is being measured in hours, right? That's going to change how I need to think about this, okay? So that's where we can also think about using this formula. Because that formula takes into consideration K is the number of compounding periods within your chosen, within the unit of time. So if it's compounding every 20 minutes, 20 minutes is 1/3 of an hour. So the population is compounding 3 times an hour. So knowing that the population is compounding multiple times an hour tells us that this is actually a better model for us to use than the f of x equals p sub 0 times a to the x. So what can we plug in? Well, K is the number of compounding periods, which is 3. And what do we know about R? Well, R is the percent change per compounding period. So every time that it compounds, like every time 20 minutes passes, it's doubling, right? Which means that we have a change of 100%. We're adding on 100% of what was there. So when it doubles, the rate is 100% change. So R would be 100%, but we have to put that in as a decimal number. So that's equal to 1. So you can see how when I was talking about that P sub 0 times a to the x, that's a good model, but it doesn't take into account the fact that it is being compounded per unit of time, right? And so we need to tell ourselves that T is in hours.
Is it always in hours?
Unless, so if, usually I will tell you, okay?
Yeah.
If I don't give you the unit of time, you can use the original unit of time.
So 20 minutes?
So minutes would
Yeah,
be,
okay.
yeah.
Okay.
So I wanted us to think about it in terms of hours because that's a weird idea to convert between it being every 20 minutes and the idea that it has to be 3 times t or 3 times x, because Again, you're relating how many times is it compounding over the hour, and that's why we have to multiply that exponent by 3. Okay. All right. I know that we are at our time. I was going to do two more explanations. If you want to stay and hear me do them, great. If you need to go, that's fine. I'm going to keep recording while I go through these two. And if you want to come back later, by later I mean tomorrow, and watch them, that's fine. So again, if you want to stay and watch me do them, you can. If not, I will teach to myself. So just wanted to give everybody the option that if you wanted to go, you could.
I'm staying.
Okay. Give me 1 second. I just want to make sure I got the rest of the people who came. Okay. All right. So next one says, given an initial population of 1,200 birds that decreases by 20% every 6 months, write a model to represent this situation with T measured in years. How long until there will be only 100 birds? So here are some pieces to pick out that are important to notice and which can kind of guide you towards which model to use. There's no mention of continuous growth or decay. So that automatically tells you do not use a continuous model, which is base E. Then because it talks about there being a 20% change, that leads us to know, okay, we need to use the model that has the rate involved in it. Meaning we want to use the model that's that periodic model, okay? So the initial population, that's P sub 0. It's telling us that the population is decreasing by 20%, okay? So decreasing means that our rate has to be negative. But again, we plug that in as a decimal. So 20% as a decimal is going to be 0.2. And then finally, that decreasing is happening every 6 months. So that means that if we think about compounding, so it takes 6 months for that 20% to reduce. They're telling us to measure in years. So 6 months is half a year. So then if it compounds every 6 months, which is half a year, that tells us that it compounds twice a year because there's 2 6-month increments within the year. So therefore, our K has to be 2. So lots of information that we can build our model with. So we've got f of x equals 1,200 times 1 plus negative 0.2 to the 2t. So we can simplify. And so now we have our model, right? So great. What do we do with this? Right? Like we wrote our model. Why aren't we done? And it's because the real question was, how long will it take for there to only be 100 birds? So again, we can go over here. Now, as I've said, I show you these tools to help you to monitor your understanding. I want to see that you can solve this with the algebra steps, okay? But if we're thinking about, we want to know when this function equals 100, that means that we are looking at two functions, right? So I'm looking at, oops. Nope, not 12,000, 1,200. Okay, so we've got, okay. There's that, and then I'm looking at when does that population equal 100? So it's gonna take 5.568 years for that population to reach 100. So again, graphing the two sides, because that's what we want it to equal, gives us a visual representation of what's gonna happen. It gives us an idea of when this is gonna happen. But again, we now need to get into the actual nitty-gritty of solving this using logarithms. And I know I have to use logarithms because my variable is in the exponent. And in order to get to that variable in the exponent, the only way to get there is by using the inverse function, which is a log. So if we look at the algebra of the situation, we've got 100 equals 1,200 times 0.8 to the 2t. So we need to divide both sides here by 1,200. So I've got 100 divided by 1,200 equals 0.8 to the 2t. We can reduce this 100 divided by 1,200 to 1/12, which 1/12 is not a nice fraction, right? So I'm leaving it as 1/12. I'm not going to convert it to a decimal. So from here, I need to take the log of both sides. And knowing that that power rule is really important because it allows us to bring that exponent down. Okay, so here is going to be, we're bringing that 2t down to the front. So I've got log of 1/12 equals 2t times log of 0.8. I know I'm running out of room. You can barely see what I'm trying to write. So how do we solve this? We're going to divide both sides by log of 0.8. Okay. Again, don't try to cancel the word logs out. Don't try to cancel the values inside the parentheses out. Just go to Desmos or your calculator. Again, I use Desmos because I think it's really nice. That's my opinion. If you want to use a graphing calculator, that's fine. Just go in and now plug this in. Again, it gives us a value, okay? And that's equal to 2t. So our last step is to divide both sides by 2. Oh, not by 1, come on. And we get that t is equal to 5.6, no, excuse me, 5.5. 6, 8 years. Oh, wait. That's what we were looking for, right? And so, again, seeing it visually, seeing where they're supposed to intersect is going to help you to monitor, am I doing the algebra steps correctly, right? Okay, last one has to do with continuous model. That's why I wanted to make sure we got to it. It says there's an initial population of 12 bacteria that grows to 360 in 20 minutes. Write a continuous model. When you see those words, I want you to automatically go, okay, f of x equals p sub 0 times e to the kt, right? Continuous goes with e. So to represent the situation with t being measured in minutes, how long will it take there to be 1,200 bacteria? So initial population, 12. Then we get 360 in 20 minutes. So time is always going to be your independent variable. Time marches on. It stops for nothing. Everything depends on time. So what that tells us is that this information is an ordered pair of 20, 360, right? That's how we want to treat that. So if we go to our model, I've got f of x equals 12 times e to the kt. Too many variables, right? This is my t value. Oh man, I got to be consistent in using my variables here. I'm going to confuse you. And this is my f of t, right? So if we plug those in, I've got 360 equals 12 times e to the k times 20. Now we've created a situation where we only have one variable. Yes, I know the letter E is there, but remember E is a number, right? We're not treating it as a variable. So we can go ahead and divide both sides by 12. 360 divided by 12 is going to be 30. This gives us 30 equals E to the 20k. And now we're in a situation where our variable is in our exponent. We have to get it out from the exponent. The only way to get it out is to take the log. Because we have e involved, we have to take the natural log. Once we take that natural log, we can bring our exponent down in front using that power rule. And because we know the natural log of e is equal to 1, we can drop that off. And from here, we can solve for k by dividing both sides by 20. And I'm going to round to 4 decimal places to be as accurate as possible. So now we know that our k value is 0.1701, meaning our growth factor, our growth rate is 17%. Okay. Why did we have to do that? Well, we have to write our initial function before we can even solve for the question that says, how long is it going to take for there to be 1,200 bacteria? We know that our initial population was 12. And so now we can put that in there. This is our general formula. That's just the function that models this situation. From here, we want to solve for when there's going to be 1,200, which means we're going to put 1,200 in for f of t. And we're going to solve for t. So I'm going to stop and let you calculate t. go ahead and send me a direct message with your answer. And then we're done for the day. I know I've gone way over and I'm sorry. Okay, so let's solve this. What do we need to do? Well, first of all, let's give ourselves some more space. Let me copy this and go to the next page.
So when you like get to what t equals,
Mm-hmm.
how does that relate to the initial 20 minutes? Like, is it so like the answer I got for time, is that the amount of minutes it takes to get there,
Yes,
or
that's
okay,
how long it's gonna take in order for it to get there.
in minutes though, right?
In minutes, yep, because we're saying that it's measuring in minutes, right? So from here, we're gonna divide both sides by 12. So we're gonna get 100 equals e to the 0.1701 t, right? Just giving everybody feedback on their answers. So from here, we're gonna take the natural log of both sides. Again, taking that natural log allows for our exponent to come down in front. Okay. Again, until you're comfortable with getting rid of that ln of e, continue to remind ourselves, oh, the natural log of e is equal to 1. That's why it drops off. That's why dealing with continuous functions is so nice. And then finally, when we plug that in, the natural log of 100 divided by we get that t is equal to 27.073 minutes. Okay. We can feel uncomfortable with what these answers are, right? Like as you were saying, Luke, you're like, what is that value? Because there is the idea of, is that a reasonable amount of time, right? So it's continuously increasing by that percentage of, so every second, every nanosecond, it is constantly growing. So again, if we look at the original function,
Yeah, it just seemed weird to me that it only took 7 more minutes for it to get to 1200 from 360.
right,
If it's
and
constantly growing, then it's growing faster and faster each time.
yes, and so that value is being compounded on top of itself, and we can see how quickly that curve grows, right? It shoots up there, and so that's how it's again, it seems weird. So we've got that f of x equals 360. Which right here, we can see that happens at about 20 minutes, right? And then we're looking at f of x equals 1200. If we continue to scroll out, again, it got so steep within that time period. So much because it's continuously compounding. So remember, exponential growth means it's multiplying continuously by that value, right? It's being raised to that. And so exponential growth gets big real fast when we're looking at that. So again, give yourself a visualization. That's why Desmos is so powerful. It really helps to drive home that idea of how that growth is happening. So, all right. Thank you to everybody who stayed. I know that I took up all of our time, and I went over. So I appreciate you staying. I will talk at you next week. In the meantime, I will be sending, not sending emails. I will be posting, right, in our announcements, the update about what we have to do next week. And I will also be sharing feedback on your quizzes and your projects tomorrow. I'm gonna get that stuff graded tomorrow, okay?
Yeah, I'm about to submit my written work for my
Okay.
quiz 'cause I didn't submit it last night.